So, going to finish off this 5.2 today, talking about the equations and graphs of sinusoidal functions. Then tomorrow will be 5.3. That'll finish off this chapter. Monday, you guys are having a quiz on chapter 5. We'll also be starting chapter 6 on Monday. And then after chapter 6, that'll be time for your next unit exam on trigonometry, chapters 4, 5, and 6. So, once again, a sinusoidal function is a function whose graph resembles the sine or cosine curve, and it's called a sinusoidal function. The graph of a sinusoidal function is called a sinusoidal graph. Many periodic phenomena have sinusoidal graphs. So we saw yesterday that the height of the tides in the ocean rise and fall, and the height of the tide or the depth of a harbor can be expressed as a sinusoidal function. But there are other ones as well. For example, the time of sunrise as a function of the day of the year. So if you kept track every day of the year, the time that the sun rose every morning, and you plotted that data, it would follow a sinusoidal function. In the same way, the time of sunset would do exactly the same thing, would follow a sinusoidal function. The height of a chair of a Ferris wheel as a function of time would also follow a sinusoidal function. Right? As the wheel goes around at a constant rate, the height of the chair off the ground will rise and fall. It will follow a sinusoidal pattern. And the depth of the ocean due to changing tides, which we've seen. So we'll look at a couple examples where the function is given, and then also where we need to write the function. Most of the equations will be functions of time, and the variable used will be t. The period of the graph will be in time units. Graphical methods will be used to solve problems, and determining a suitable window is an essential feature of the solution. So here's another example where we're talking about the height of the water in a harbor. It changes due to the changing of the tides. So in this case here, that depth is defined by d at t equals 12 plus 5 cos 0.5t, where t is between 0 and 24 hours. And again, this gives us the depth in the depth meters of the water in a harbor, t hours after midnight. Now, the first thing we would probably do here is change the equation into the format that we're used to working with, meaning that it follows the order of A, B, C, and D, where A is the number in front of the sine or cosine, so that's 5. Cos, this equation has a B value. It's the number directly in front of the x, or in this case, directly in front of the variable t. There is no C value here. This graph has not been shifted horizontally, but it has a D value of plus 12. So that constant of 12, normally when we write our equation, is written at the end. So from the equation, we're going to determine the min and max depths of the water in the harbor. And there is a bit of an equation we can use to determine that, which is something that we really have been doing without talking about it as an equation. Because remember, when we graph these, we always started with the horizontal midline, which in this case would be plus 12. And then the amplitude of this is plus 5, which means that the maximum height of the graph will be found by starting on the horizontal midline and adding the amplitude. Our maximum can be found by going d plus a. D is the horizontal midline. It tells you where that middle value is. And the amplitude tells you how high above that horizontal midline you go to get the maximum. So in this case here, it'll be 12 plus 5, which is 17. The minimum can be found by going d minus a. And again, we have essentially been doing this when we graphed our sinusoidal functions. We started with that horizontal mid value, and we subtracted the amplitude to get to our minimum point. So really we went d minus a, and 12 minus 5 here would be positive 7. So these are the max and min values. These are the numbers that we used when we graphed it in our calculator. These are the numbers that we use for our y min and our y max. They tell us the range of the function. Part B says to determine the period. The period, remember, is always found by going 2 pi over b. When we are talking about our period, we're always going to work in radians unless we're told specifically that we're in degrees. So in most cases, we'll be working in radians. So in this case here, our b value is 0.5. And so if we go 2 pi divided by 0.5, that gives us a period of approximately 12.57 hours. .566 becomes 12.57. And yesterday we saw an example where the period was 12 hours. I said it's a little bit more than that normally. And we also saw examples where the period was 13 hours. And I said it's going to be a little bit less than that normally. So this is a more accurate estimate for the tide cycle. It's not regularly every 12 or 13 hours. It's somewhere in between. Okay, so every 12.57 hours, the tide will go through one cycle. A few years ago, I hiked the West Coast Trail. So that's along the west coast of Vancouver Island. And there were times where we had to have our tide tables because a lot of this hike was, well, not a lot of it, but some of it was done on the beach. And so as the tide was coming in and out, you had to be aware of that, especially if it was coming in. And there was one place where we hoped to stay on the beach and go around this point, but the tide was coming in too fast. We didn't get there in time. So we were cut off, and we had to kind of go up and over through the bush to get to the other side of this point. Right? So, and as we saw yesterday, in some of those harbors and some of the bigger ships that are in there, they need to be aware of those tides that are changing. Otherwise, they could get stuck in the harbor. They could run aground as the water goes out and the depth of the harbor goes down. So it is something that, depending on what you're doing on the ocean, you need to be aware of. So part C says, what is a suitable window that could be used to display the graph of the function? So when we talk about the windows, we talk about two things. First, the x values. And I think we talked a little bit about this before, that if you were ever asked to do a graphical solution on the diploma exam, one of the things that you would need to include would be the windows that you used in your graphing calculator. You need to have the equation or equations that you're putting in there. You need to have the windows that you're using, and then also an explanation of what you did on your calculator to get the answer, whether it's the x-intercept or intercepts, or maybe the point of intersection between two graphs. Okay, but the period will help us determine what the windows need to be. If we need to see one cycle of this graph, our x min and max must include at least 12.57 hours. So maybe I might go from a minimum of -1 to a maximum of 13 and a scale of 1. Okay? And I'm choosing these numbers because our period is 12.57 hours. And the reason we might start at -1 instead of 0 is that if you start at -1 on the x-axis, then you will clearly see where the y-axis is. It won't be right along the edge of your graph or the edge of your window. And then for our y min and max, that's where the min and max that we calculated in part A comes in. Right? This graph has a minimum value of 7, a maximum value of 17. So maybe we might choose to go from 6 to 18. And maybe a scale of 1 or 2. It doesn't really matter what the scale is. Yes, sir. Put it in what? Well, probably wouldn't work very well because the period of this is only 12.57 hours. Okay, so you wouldn't know unless you tried it. Okay? You wouldn't know. But you'd want to see at least one cycle of the graph, so your windows would have to be set to include that. If it was a case where you're using the graphing calculator to solve an equation, as long as your windows contain where that solution is, you're fine. All right? So then it says, what is the depth of the water to the nearest tenth of the meter at 2 a.m.? So there's a couple different ways you could do this. Remember that T is the number of hours after midnight. So at 2 a.m., that'll be 2 hours after midnight. So one way to do this would be just to use the equation and let T equal 2 in that equation. So it'll be 5 times the cosine of 0.5 times 2 plus 12. So you could use this equation with your calculator, again, in radian mode. You'd only be in degrees if you're specifically told that. Otherwise, you're in radians. So it'll be 5 times the cosine of 0.5 times 2, which is 1. So you could just put 5 times the cosine of 1 plus 12. So that would be the depth of the water in meters, approximately 14.7. It does say to the nearest tenth. So this can be done using the equation and subbing in the value of t. But our other option would be to use the graphing calculator. We can put this equation in there. So again, it's 5 times the cosine of 0.5x, close the bracket, plus 12. We've already set what our windows should be, right? Our x, we're going from -1 to 13. And I chose a scale of 1 there. For y, I'm going from 6 up to 18. And again, I put my scale at 1. Maybe I'll change it to 2. But using a scale of 1 wouldn't really matter. So now when we graph it, we see one complete cycle of this graph. And we want to know what the depth is when t, or in this case, x is 2. So we go into the trace mode, go to enter, and you get exactly the same answer, 14.7 meters. So you can either use the equation in your calculator or the graph on your calculator to get that answer. Part E, a ship which requires a minimum of 8.5 meters of water is in harbor at midnight. By what time to the nearest minute must it leave to prevent grounding? So we did this on our calculator yesterday by doing the second equation, in this case, y equals 8.5. It'll draw that line, and we need to find that first point of intersection. Second function trace, number 5 for intersect, enter, enter. I'll put my guess at 5 hours, and it's actually at 4.69 hours. Okay. And again, you can always make sure by getting out of there and going x enter, it gives you the last value of x that was in your graphing calculator, just in case it's kind of small to see on the bottom of the grid. So now this is the number of hours. The question says by what time to the nearest minute. So again, t is approximately 4.69 hours, but that's an approximation because to write it down you had to round. But if we go back to our calculator, we know that that is between 4 a.m. and 5 a.m., closer to 5 a.m. because 0.69 of an hour is going to be closer to the next hour than the previous. So we can find out what the time is on our calculator. Okay. So again, it's 4 a.m. and a certain number of minutes. And those number of minutes can be found by taking that 0.69. But I want to use the entire decimal, so I'll get rid of the 4. So I just have the 0.69 and then multiply that by 60 because there's 60 minutes in an hour. So to the nearest minute, that would be 4:42 a.m. when you round to the nearest minute. That 41.5 minutes would round to 42. And then part F, what is the next time to the nearest minute that the ship can return to the harbor? So when we look at our graph now, we want to find that second point of intersection. Second function trace, number 5 for intersect, enter, enter, and maybe I might put hour 7 in here, and it's actually looks like 7.87, but let's quit out of there and bring it back this way. So yes, 7.87 approximately. 7.87 hours after midnight. So again, that is almost at 8 a.m. Right? It's after 7 a.m. but not quite 8 a.m. So we can again find out how many minutes 0.87 of an hour is by getting rid of the 7 in front and then multiplying that by 60. And to the nearest minute, it would be 7:52 a.m. is when the ship can return to the harbor. So here's one dealing with time of sunrise. In a certain town in Alberta, this equation can be used to find the time of sunrise, where D is the day of the year. T is the time in hours after midnight that the sun will rise, and D is the number of the day of the year. Now, once again, we would probably rewrite this equation a little bit so it's in the form that we're used to dealing with. So we've got our A value first, times the sign. Now our B value, that will be the coefficient of what's in front of the brackets. Inside the brackets there is D minus 78. That's what's inside the brackets. So B is the coefficient of that, which would be 2 pi over 365. That is our actual B value. Our C value is 78, so the graph would shift 78 to the right. And our D value is 6.3, so that is our horizontal midline. That's like the average time of sunrise for the year. 6.3 hours after midnight. But part A says, what is a suitable window that we could use to display the graph of the function? So there's two things that we need to do before we can set our windows. To find our x windows, we need to know the period. So let's start with the period. The period in this case is 2 pi divided by b. So you're going to divide by 2 pi over 365. And to divide by a fraction, you multiply by the reciprocal. So you're going to multiply by 365 over 2 pi, and the 2 pi's will cancel, and you're just left with 365. Which makes sense because that's how many days there are in a year. So it makes sense that that would be the period. So our x windows, we could go from, let's say, negative 10 to 370. Just so we can clearly see the y-axis and one full cycle of the graph. And maybe we set our scale at 50. So every tick mark along the x-axis will count for 50 days. To find what our y windows will look like, we need to know the min and the max of this function. Remember, the min is found by taking d, which is 6.3, and subtracting a, the amplitude. Subtracting 1.79. So 6.3 minus 1.79. There's our minimum, 4.51. And our maximum is d plus a, 6.3 plus 1.79. 8.09. So for our y min and max, maybe we'll go from 4 up to 9. Our Our actual minimum is 4.51, so we go a little bit less than that. Our maximum is 8.09, so we'll go a little bit greater than that. Use the formula to determine to the nearest minute when the sun rose on May 27th, or May 7th, excuse me, which is the 127th day of the year. So using the formula, t the time would be negative 1.79 times the sine of 2 pi over 365 times 127 take away 78 plus 6.3. So again, we need to be in radian mode for this. Negative 1.79 times the sine. So we're going to have another bracket here to go 2 pi over 365. Pi over 365. So close a bracket on the b, then open another bracket for the 127 minus 78. Close a bracket on that, and then close the bracket on the sine of all that, plus 6.3. So at hour 4.96, which is almost 5 a.m., so to the nearest minute, if we get rid of the 4 again and just deal with the decimal, that's multiplied by 60 minutes. That's how many minutes there are in an hour. So it'll actually be at 4:58, so almost 5 a.m. So that's what time the sun would rise in this town on May 7th. Determine on which days of the year the sun rose at 7 a.m. So to do this one, you would want to have the equation in your calculator and the window set to what we have them at. So it's negative 1.79 times the sine. Again, we'll need another set of brackets for our b value, 2 pi over 365. And then another set of brackets for x minus 78. Close the bracket on that and close the bracket on the sine. And then our plus 6.3 on the outside. We want to know when the sun rose at 7 a.m. So that would be my second graph. The line y equals 7. Again, we've said what our windows would be. X is going from negative 10 up to positive 370. So we can see one complete cycle. And we set our scale to every 50 days. And y, we're going from 4 up to 9 and a scale of 1. So there's a sinusoidal curve. And then the line y equals 7. We need to find those 2 points of intersection. Thank you. So the one on the right is approximately day 284, it looks like. The one on the left, I put day 50 as my guess. It's actually day 55 to the nearest day. Right, and while you have the equation in there, you can also go back and check the answer we got for part B. So if I go into trace and I make sure I'm on the sine graph, which I am, I know that because that's the equation that's displayed at the top. If I let x equal 127, it gives me that 4.96 decimal for y. So we did it using the equation. We could also confirm it by using the graph in the calculator. All right. So the graph shows the height, meters above the ground over time, t in seconds that it takes a person in a chair on a Ferris wheel to complete 2 revolutions. The minimum height of the Ferris wheel is 2 meters and the maximum is 20. Right? So our minimum there is at 2 and our maximum is at 20. How far above the ground is the person as the wheel starts rotating? So you read that right off the graph. It looks like that number is 11 meters. 11, 12, 13, yeah, there's a scale of 1 there. So it looks like that is at 11 meters. And then it says it takes 32 seconds to make 1 complete rotation. Determine the equation in the forms if it's a sine function as well as if it's a cosine function. And a is greater than 0. And it doesn't say that, but we always use the minimum possible phase shift. Okay, so before we can write the equations, there are some things that we need to know. Right? We've seen before that our d value can be found by determining the horizontal midline. And that horizontal midline is like the average between the max and the min. So how could we find that, Vish? How do we find the horizontal midline? So what's the maximum? Yeah, it'd help if you're on the right question, and it would help if you're following along. What's the minimum? So what's the horizontal midline? About 11. You want to go double or nothing on the pops that you owe me? What do you think, Cedric? Or Logan, sorry? How do we find the horizontal midline? Sure. But how far in between them? Yeah. A deal? And you're going to bet a pop on that. Okay. So the distance between the two is 18 units. And halfway, what's that? You changing your answer on us? So the distance between the max and the min is 18 units. Half of that is 9. So the middle is 9 units below the max or 9 units above the minimum. So it is at 11. Should have bet, Vish. Josh, question? Okay. So you see that? The maximum is 20, the minimum is 2. That's a distance of 18 units. The horizontal midline is halfway in between them. 9 units away from each of them. If you go 9 units below 20, you're at 11. 9 units above 2, you're at 11. Okay, so that's where this graph is starting. That's where our horizontal midline is. And that is our d value. Okay. So Chase, what's our amplitude? 9. That's the distance from the middle up to the max or the middle down to the low. So our amplitude, which is our A value, is 9. All right. How do we find our B value? Tyson? How do we determine what B is? Sure, you can go from one maximum to the next. That would be one way you could do it if you're reading it off the graph. Or you could go from where the graph starts, it's going upwards through the horizontal midline to the next place it happens, it's over here. But also, if you look at the question, it tells us that I thought it said something about, oh yeah, it takes 32 seconds to make one complete rotation in part B. It tells us that. So that means the period is 32 seconds. And remember that the period is 2 pi over b. Our period here is 32, or 32 over 1. That must equal 2 pi over b. When you cross multiply, you'll get 32 times b equals 2 pi. And so b would be 2 pi over 32. We've used this relationship a couple times now in order to determine our b value. And every time when you set this up, this relationship, where period equals 2 pi over b, and you cross multiplied, and then you got b by itself, in every case you ended up dividing 2 pi by the period. Our original formula that we started with is that period equals 2 pi over b. If you have the b value, you plug it in, you'll get your period. But if you have the period and you want to find the b value, you set it up, you cross multiply. In every case, we ended up dividing 2 pi by the period. So what that means is this relationship that I've boxed in blue, you can switch the period and the b around. B is equal to 2 pi over period, as well as period equals 2 pi over b. Every time when we were given the period and we wanted to find b, we set up this relationship, we cross multiplied and then got b by itself. In every case, we divided 2 pi by the period. So here, b is 2 pi over 32, which would be pi over 16 if we reduce it. Right, so there is our b value. So to write our equation of the sine graph, remember sine starts in the middle heading upwards. If we're going to write this equation as a sine graph, there is no phase shift. There is no c value. Okay, so for a sine function, our a value is 9. Our b value is pi on 16, so it'll be pi on 16 times t, and our d value is plus 11. If it's a sine function, remember that sine starts in the middle heading upwards. That's where this graph is starting. It's starting on the horizontal midline heading upwards. So for a sine function, there's been no horizontal shifting or no phase shift. Or we could say c is 0. But for a cosine graph, there would be a phase shift. Because remember, cosine starts at the maximum, which would be right here. So it shifted over to the right. Now, we need to figure out what that horizontal phase shift is. Remember that for a sine or a cosine graph, there are 4 critical points in every period. You don't start counting the critical points until you move, but if we look at this graph, our first one will be where we start. That's where we're starting. So the first one, I suppose, would be at the first maximum. So there's our first one. Then to the middle, there's our second. Then to the minimum, there's our third. And then back to the middle, the starting point, there's our fourth. So there are always 4 critical points in each period. In this case here, our period is 32. Our critical points could be found by taking the period and dividing by 4, which is every 8 hours, or 8 minutes, I should say. So that tells us that the cosine graph would have been shifted 8 to the right, because that is where this critical point occurs. It occurs after 8 minutes. And again, we got that because we know there are 4 critical points in every cycle of the graph. One full cycle is 32 minutes. Divide by 4. So every critical point will be 8 minutes. So that tells us that our C value, if it's a cosine function, will be positive 8. It'll be y equals 9 cosine. And again, it'll be pi over 16 bracket t minus 8 plus 11. And like we did before, we could put both of these equations in our calculator. We could make sure that we get the same graph. And then we can also check some of the key points that are on the graph that we were provided. So let's do that. My first equation would be 9 times the sine. And I'll have to put in brackets pi over 16 times t or x. And I guess we don't need a second set of brackets for this one because there is no c value. But to put my b value in along with the variable, I'll go pi times x over 16. Close the bracket, and then you have plus 11. So there's a sine graph. If it's a cosine graph, it's 9 times the cosine. And in this case, we'll have to do an extra set of brackets because we have a b value, which is pi on 16, and a c value of 8. So we'll put the pi on 16 in brackets, and then another bracket for the x minus 8. And then plus 11 at the end. We didn't state our max and min values, but we've got the graph provided for us, so we can get what our window should be right from that. Okay? So if I go from, let's say, -5 on the x-axis up to, let's say, positive 65, so I get 2 complete cycles, and I can do a scale here of 5. For y, we can go from, let's say, -2, so we can clearly see the x-axis, up to positive 22 on the y-axis. And maybe we'll have a scale there of 2 as well. So it did them both really fast, one over the other, so we know our 2 equations are equivalent to each other. But we can also check to make sure that this graph in our calculator matches the graph on the page by going into the trace mode. And if we let x equal 0, that's our starting point, 0, 11. We said our critical points were every 8 minutes, so at 8 minutes we should be at our maximum, which is at 20, and we are. Another 8, which is 16 minutes, we're back to the middle of 11. Another 8 would be 24 minutes, we should be at our minimum of 2, and we are. Right, so we've just shown that the graphs in our calculator match the graph on the page, and the graph on the calculator came from the equations we came up with, so they're correct. Okay, so we can always check these. Find the distance the person is from the ground to the nearest tenth of a meter after 30 seconds. So we can do this on our calculator by going into our trace mode and letting x equal 30. And I guess time is in seconds, not minutes. So we can see approximately 7.6 meters. Could also get that by using the equations that we came up with and letting t equal 30. How long after the start of the ride does it take for the person to reach a height of 5 meters to the nearest tenth of a second? So for this, we'd have to do a second or a third equation, I guess. Y equals 5. And then find the point of intersection. This first point over here. The second function trace, number 5 for intersect, enter, enter. And maybe I can put my guess at around 10 seconds. Oh, I know what I did. Try this again. So my first curve will be the sine graph. My second curve would have to be the line y equals 5. So I need to go down with the arrow to go to y equals 5. There we go. And now I can slide over to that to get as close as possible. And so our answer is approximately 19.7 seconds. That's the x value there. Okay. A nail is caught in the tread of a rotating tire at point N. In the following sketch, the tire has a diameter of 50 centimeters. So that means a radius of 25 centimeters. And rotates at 10 revolutions every minute. After 4.5 seconds, the nail touches the ground. So it goes 10 revolutions every 60 seconds. So if you divide top and bottom by 10, that means it's going to go through one revolution in 6 seconds. So that is the period. The period is 6 seconds. The period is how long it takes to go through one revolution. So if we draw in our horizontal midline here, and we know that it will be at N, because N is in the middle of the circle. It's halfway up from the bottom. And we know that it takes 6 seconds to go through one cycle. That is our period. So this graph started on the horizontal midline heading upwards. I've marked the point on the grid there where it gets to that same point again. And we determined, because it's 10 revolutions in 60 seconds, that means one revolution in 6 seconds. So that is our period. Now remember, the critical points. There are 4 critical points in every rotation, in every period. Our critical points will be at 6 seconds divided by 4, or every 1.5 seconds. So that means if we start at time 0, after 1.5, we'll be at the next critical point, which is a maximum. Another 1.5, which is at 3 seconds. We're at the next critical point, which is back to the middle. Another 1.5 seconds, which is 4.5. We're at the next critical point, which will be the minimum. And then another 1.5 seconds, which takes us to 6 seconds. We're at our final critical point in the first cycle, back to the middle. So we've already answered part A. We've used the information given to write a scale for the x-axis. Now we will do the same thing in the y-axis. Because the diameter is 50, right? It'll go from 0 up to a maximum of 50, which means the horizontal midline is at 25, halfway up. So we've now completed part A. We've written a scale for each axis. And now we want to write the equation for the height of the nail as a function of time, whether it's a sine or a cosine function, and A is greater than 0. And once again, we'll use the minimum possible phase shift. So if it's a sine function, there is no C value, because the graph of sine starts in the middle heading upwards, where this graph, that's what it does. But we need to know our A value. A is the distance from the horizontal midline to the max or to the min. That is positive 25, which is also our D value, because our horizontal midline is at positive 25. We are told that, or we know that it does one revolution in 6 seconds. So our period is 6 seconds. Remember that we can find our B value by going 2 pi over the period. So it's 2 pi over 6, which is pi over 3. That is our B value. So if we're going to write this equation for a sine function, it'll be 25 sine, and it'll be pi over 3t plus 25. We determined our B value to be pi on 3, and our D value is plus 25. If it's a cosine function, now we're going to have a phase shift. Normally the graph of cosine starts at the maximum. In this case, that occurs after 1.5 seconds. Normally the graph of cosine starts on the y-axis at the maximum. This is shifted to the right 1.5 seconds, so that is our C value if they were writing a cosine function. So there's the equation if it is a cosine function. And we can put both of these equations in our calculator to check. So the first one is 25 times the sine of pi x over 3 plus 25. The second one is our cosine function, 25 times the cosine. And I'm going to have pi over 3 in brackets for my b value because I have to have a separate bracket for my x minus 1.5. Close both brackets and then put the plus 25 at the end. If we look at the graph that we're given, that will tell us what that along with the scale that we have figured out will tell us what our windows should be. So if I want to see, say, 2 complete revolutions, maybe I'll go from -2 on the x-axis. It does 1 revolution in 6, so 2 revolutions in 12. So maybe we'll go up to 13 just so we clearly see the complete revolutions. And I'll set my scale to 2 here. For y, I'm going to go from, let's say, -5 up to 55 and a scale of 5. So now when I graph it, it drew both curves, one over the other. So we know that our 2 equations match each other. To make sure it matches this graph, if we go into trace and we start at time 0, we're in the middle at 25. At time 1.5, we're at our maximum. At time 3, we're back to the middle of 25. And at time 4.5, we should be at a height of 0, and we are. So not only do our 2 equations match the same graph, but the graph matches what it should match, meaning the one that we were given. So how far to the nearest tenth of a centimeter is the nail above the ground after 6.5 seconds? So we can do that on our calculator. That is by far the easiest way to do it. After 6.5, the height is 37.5 centimeters. Yeah. So h at 6.5 is 37.5 centimeters. And you could also get that from the equation by letting t equal 6.5. Okay, you could also get it from that. All right.